Hello everyone. So today we will see CCP module of the PIC microcontroller 18 PIC18F4550. Okay. In the last session we have discussed ADC module of the PIC18F4550. Okay. Today we shall discuss PWM mode of CCP for PIC18F4550. All of you know that PIC18F4550 has two CCP modules which are used for three purposes: capture, compare, and PWM. Okay, so these two modules are used for capturing the external events, for comparing the two values, and third one is for driving DC motors, for driving LED displays. This PWM mode is also available in PIC microcontroller. Okay, so by varying the PWM width, we are going to control the speed of the DC motor, or we are going to drive DC motor. Okay, so all of you know that what is PWM. In digital communication, you have used pulse width modulation number of times. So pulse width modulation is the modulation in which width of the pulse is changed in accordance with the information signal. Simply we can define it. Okay, so this particular PWM section of CCP module today we are going to discuss. Let's start with the session. Okay, so objectives of this session are: first we will study what is PWM. Second, we will study on chip CCP module which is available for PIC18F4550. Third, here we are taking one example of DC motor driving. Okay, so DC motor is interfaced with the PIC microcontroller by using L293D driver IC. Okay, so because output current of the PIC microcontroller is as small as compared to DC motor requirement. Okay, so to drive this DC motor, we need to boost the current which is coming from the PIC microcontroller pins. Okay, for that purpose, driver IC L293D is used. Okay, and in the last section, we will see apply a PWM signal to control the speed of the motor. That we will set PWM period and duty cycle for controlling the DC motor speed or driving DC motor. Okay, let's start with the CCP module. Okay, depending on the PIC version, there are 1 to 4 CCP modules which are available in PIC18 series microcontrollers. Okay, as we talk about PIC18F4550, it has two CCP modules which are available for capturing, comparing, and PWM outputs. Okay, so these CCP modules contain 16-bit register which can be operated as a 16-bit capture register, 16-bit compare register, and PWM master slave duty cycle register. Okay, here 16-bit values, that means 65,000 clocks. In simple words, we can say that in capture mode, 16-bit capture register is there, so we can measure in terms of clock signal 2 raised to 16 clock inputs, okay, which are unknown to microcontroller, that can be captured by using this particular register. In same way, compare register, if we want to generate something from the microcontroller, that means if any event we want to generate from the microcontroller, then we can load the 16-bit values in compare register. Okay, and upon comparison match, microcontroller will generate an event that is required for the user or as per the user needs. And in third PWM, here we are going to generate duty cycle output. Okay, controlled duty cycle output to drive the DC motor. Okay, so for this controlling CCP modules, two resistors are given. One is control resistor and second one is data resistor. Data register has two bytes. CCP are higher byte and lower byte. Okay, if we are going to have CCP module 0, then CCP 0L, CCP are 0H. These are the two registers belongs to CCP module 0 and 1. For 1, we can say that CCP R1L and CCP R1H. These are the two registers which are allocated for CCP module 1. Okay, that is second module. So for this CCP module, timers are very important. Okay, for capturing and comparing purpose, or for capture and compare mode, timer 1 and timer 3 are used. For PWM output, timer 2 is used. Okay, and as far as pin is concerned, RC1 and RB3, these are the two pins which are available for CCP module. Okay, so we will discuss this particular pins later. Okay, first we will see what are the applications of capture mode, compare mode, and PWM mode, that is of CCP modules. Here you can see capture mode can measure event arrival time recording, period measurement, pulse width measurement, interrupt generation, event counting, time reference, duty cycle measurement. These are the applications of capture mode. In case of compare, you can generate an event, okay, by using comparison of two values. Okay, upon compare match, okay, you can generate single pulse, train of pulses, periodic waveform. You can start ADC conversion that we have seen, and you can set time reference for the comparison purpose, or for comparison. In third PWM mode of CCP module, here CCP pin is used to produce 10-bit resolution PWM output for controlling the speed of the DC motor or for driving the LED displays. Okay, so 10 bit 1 byte register is there, and remaining two pins, fifth, 5 and 4. These sixth and fifth pin are from CCP1 control register, or CCP 0 con register is used for setting the duty cycle of the CCP PWM model. Okay, so let's start with the PWM block diagram. Okay, so here you can see two comparators are given for generating PWM output. Here PR2 register, that is the period register of PWM. This is the 8-bit register which is used to set the duty. Sorry, it is used to set the period of the duty cycle. Sorry, PWM output. So here you can set period, total period, that is on time and off time, can be set by loading the 8-bit value in period to register. Okay, these two values. Okay, another value we will store in timer 2 register, and we will turn on timer 2 upon compare match. This particular comparator will set the RS flip flop to high. Okay, that will generate PWM pulse period. Okay, or PWM signal. Okay, and we will load the duty cycle period in this particular register. CCP R1L lower byte register will be loaded to set the pulse width of the PWM output. Okay, so upon compare match, this particular value is transferred to CCPR1H, which is the slave register. This is acting as a master, and this again will be compared with the timer 2. Now this value transfer will happen only when period of the PWM pulse is ended. At the last, or at the end of period at the end of period of PWM, this particular value is transferred to this, and this will compare with the timer 2 to start with the next cycle. Okay, so important registers are period register, timer 2 register, CCP are lower byte and higher byte register. Okay, and these two bits. Okay, because we said that 10-bit resolution is available for PWM output. So CCP R 1L is 8-bit register, 1 byte register, and remaining 2 bits are used from this particular register. CCP1 con register 6th and 5th bit, that is 5 and 4. So we can write values for this bit also, these 2 bits also. Okay, so total 10-bit resolution PWM output is available from this. Now two comparator. This is the comparator which is used for period register and timer 2 comparison. Okay, and this is the internal comparator which is available for comparing the content of CCP1 higher byte register and timer 2. Okay, here you can see 8-bit timer is concatenated with the 2-bit internal clock. Okay, 2 bits, these 2 bits of the prescaler to create 10-bit time base. Okay, so our PWM runs on 10-bit mode. Okay, so you can see here RS flip flop is there, and that sets and resets the output. Okay, on pin RC2 CCP1. Okay, RC1 and RC2, these two pins are used. Okay, so here you can see this particular pin is also available, and alternative to this RB343. Okay, this is for one and this is for second CCP module. RC2 pin is used. Okay, so here you can see the waveform of PWM output. Here you can see it. Timer 2 and PR2 values are equal, then timer resets and PWM goes high. Here PWM output will go high whenever timer 2 and period 2 value becomes equal. Okay, upon comparison match, timer will reset and it will set the PWM output to high. Okay, so at the end of this period, okay, here what will happen, this CCP1RL value will be transferred to CCP1 higher byte register, so that next cycle will start. Okay, this is the total period of the pulse. Okay, and here you can see PR2 will decide this total period. Okay, PR2, we need to load the value into PR2 for setting the period of the PWM output, and duty cycle we can set here by using this CCPR1L register and the remaining 2 bits from the CCP1 con register. Okay, so like in this way PWM output is generated by using these two comparators. Okay, of comparison between timer 2 and PR2 and timer 2 and CCP1 CCPR1H higher byte register. Okay, in this prescaling option is available with the timer 2. Okay, so that we can maximize the signal output. Okay, pulse or period for the PWM. Okay, so here you can see 3 pins are available. Okay, this RC1 is has alternative of RB3, that is port B, fourth pin is alternative to RC1. Okay, so so here you can use RC2 CCP1 module first module and CCP2 second module, that is having fixed RC1 and RC2 pins. These pins should be set to output mode, okay, by configuring by writing value 00 to these two pins. Okay, so this is an alternative to CCP second module. Okay, you can use this if RC1 is not available for the user or you. Okay, so we will see the PWM register map. Okay, here you can see number of registers are available for controlling the PWM output, for generating the PWM output. Here first is CCP1 con register, which is acting as a control register and which has address FBD. Okay, next two registers are given for writing the values into this particular registers. Okay, data registers. Okay, in which we can write value only to 1L register, lower byte register, and that can be transferred to higher byte register. CCPR1H, that is higher byte register, is not available for the user. Only CCPR1L is available for the user. Okay, which has addresses FE, FBE, and FBF. For second module control, CCP-con2 register is available, which has address of FBAH. For that, another two registers are there, CCPR2L and CCPR2H. This is lower byte and this is higher byte register, out of which only this lower byte register is available for the user. Okay, user can write value 8-bit value into this register to set duty cycle of the PWM output. Okay, so this particular register belongs to timer 2. Timer 2 control the register. Okay, here we can set the mode of selection, a pre-scaling option, post-scaling option. Okay, for by using this timer 2 control the register. Timer 2 is of 8 bits. Here you can use for setting the period of the PWM output. This will be compared with the PR2 value. Okay, so PR2 is the period register which is used for setting the period of the PWM output. Now here two terms we must know, that one is duty cycle, that is T on by T. Okay, T on by total T, that is T on plus T off. Okay, and if we are setting 50% duty cycle, that means what, T on will be equal to T off. Okay, that will give us 50% duty cycle, and in this period register we will set the period of the pulse, that is on period plus off period. Pulse period we can set by writing value to PR2 register. Okay, so let's see one register, all the registers which are controlling the PWM output one by one. Okay, so here you can see standard CCP1 control register. Okay, these 8 bits are same for CCP1 con and CCP2 con. Okay, control register. Here you can see these 4 bits are given for compare mode, capture mode, and PWM. Okay, by writing values we can set the modes of CCP module in capture, compare, and PWM modes. Okay, and these two values are for setting the duty cycle. Okay, DCB 0 and DCB 1. Okay, so let's this these two PWM duty cycle bits are given. Okay, these are unused in compare and capture mode. Okay, only PWM mode uses these two bits. Okay, because we have 10-bit resolution for PWM output, so 8 bits from the lower byte register and remaining these 2 bits are written for PWM duty cycle, and these 4 bits are used for setting the mode of CCP module. Okay, if I write 000 to all these 4 bits, then CCP module is disabled. Okay, we cannot use, we are not going to use, that means we are not going to use CCP module. Okay, second is reserved, and you can see here starts the modes. Okay, if I write 0010 to this particular 4 bits, these particular 4 bits, then I will select compare mode. Okay, now here options are available. Toggle output on match, whenever two register values are compared. Okay, and upon compare match we are generating pulse that will toggle on match. Okay, so high low output we can generate here. If I write 0100, then capture mode, upon every falling edge of the clock signal this particular event will be captured. Okay, rising edge, next mode, upon fourth rising edge, 16th rising edge, these are the modes for capturing the unknown signal which are fed to microcontroller. In simple words we can say that. Okay, if we are giving unknown clock signal, then this can be measured on every falling edge, every rising edge, every fourth rising edge, every 16th rising edge. Okay, and for comparison these modes are given. This is the first one, this is the second one. Initialize CCP pin low, on compare match force CCP pin high. This is what we are going to do with this particular mode 1000. Okay, so initially CCP pin will go low, active low signal is available on this pin, and upon compare match this particular pin will set to high. Okay, it will indicate that this comparison match is done. for given values. Okay. Next is one not one. Exactly opposite operation will perform by using this particular mode. Next mode 1010, it will generate a software interrupt upon compare match. Okay, and this interrupt flag which is allotted for CCP module will be set to high and CCP pin reflects IO state. Okay, here we can generate interrupt signal by using this CCP module in compare mode. Okay, by writing these values, we will generate an interrupt signal for microcontroller. Next 1011. Okay, here trigger a special event, reset timer, and start A to D converter. This particular mode is used for A to D converter. Okay, if we are going for comparison mode, we are comparing two values, and on the comparison match, if we are using ADC module of the PIC microcontroller, then this mode should be used. Okay, what will do this particular mode will generate a special event, it will reset the timer, and it will start A to D conversion on CCP P to match. Okay, in this again, CCPIF interrupt flag will be set to high. And last mode is PWM that we are talking about today. 11XX. This particular mode is used for generating the PWM output. This is the timer to control the register. Here you can see post scaling option and pre scaling options are available for multiplying your period of the timer. Okay, so both options are available here. Generally 0 1 s to 1 1 s to 4 1 s to 16. For post scaling also 1 s to 1 1 s to 16. These post scaling and pre scaling options are available, and this particular bit timer to on is used for turning on the timer. Whenever I write 1 to this particular bit, timer 2 starts or timer 2 is turned on. Okay, and if I write 0 to this, timer 2 should be off or it will turn off. Okay, this is timer to control the register. Here you can see timer to control the register. Timer 2 module has this particular diagram, internal block diagram or internal diagram of timer 2 module. You can see here pre-scaling option. You can see FOC by 4. This is the main frequency that will be used. Okay, for timer 2. Again, it will get divided by 1 s to 1, 1 s to 4, and 1 s to 16. Okay, these are the pre-scaling options we are available. Okay, here we will set the pre-scaling option. Then we will write timer 2 values, and comparison will happen in between period register and timer 2 register. Okay, for setting the pulse width and duty cycle, pulse cycle, pulse width cycle, or PWM cycle of the CCP module. Okay, so here again you can multiply this by using post scaling option. 1 s to 1 to 1 s to 16 options are available, and here you can use timer to interrupt flag for overflow of the timer 2. Okay, so whenever this particular flag set to 1, that means what, timer 2 has overflow. Okay, that will reset the timer 2 and we can load again timer 2 initial values. Okay, so here these are the options which are available for timer 2 module. Okay. Okay, so if I want to program PWM mode of the CCP module, then I should follow these steps. Here first we will set the PWM period, then by writing value to PR2, then set the PWM duty cycle by writing values to CCP R lower byte register and DCB0 DCB1 bits of the CCP1 con register. Okay, then in third step I will configure RC1 or RC2 pin as a output. Okay, if I want to go if I want to use RC2, then I will write RC2 is equal to 0 cross 0 0 uh, for whole port or single pin. Also configuration is available in this particular microcontroller, so we need to configure this port pin as a output pin. Okay, and in the next step I will select pre-scaling value for timer 2. Okay, So this will get increase, or this will maximize the period of the duty cycle. Okay, and here we will select the PWM mode module configuration by writing these 4 bits values with 1 1 cross cross. Okay, PWM mode is selected. Here the formula is given for setting the PWM period. Here you can see PWM period is equal to PR2 plus 1 into 4 into TOC, oscillator period. Okay, here FOC by 4. So here 4 into TOC, that is taken into consideration, and these are the pre-scaling option to increase the timer period or PWM period. Okay, so if we take example, for example, we use 20 megahertz clock frequency and output frequency is 2 kilohertz. That is the PWM frequency. Then PWM frequency will be period will be not 5 point 0.0005 seconds. Okay, so here you can see zero point 0.5 millisecond period we need to generate for 2 kilohertz frequency. So we will put this particular point 0.5 millisecond period into this formula to calculate the period register value. So here by calculating this, we will get PR2 decimal value of 624, and his hexadecimal value will be loaded into this 270. Okay, so we need to write this PR2 with value 0 cross 270. Now here we will set the PWM duty cycle. To set the duty cycle, PWM duty cycle is specified by writing values as we discussed earlier. CCP1RL, CCPR1L or CCPR2L. This these registers will be written, okay, to set the duty cycle of the PWM output. Okay, and the remaining 2 bits from the CCP1 con register are written to set the duty cycle of the PWM period. Here we can say that 10-bit resolution is available for PWM output. Okay, so CCP1 lower byte register will be loaded with the higher 8 bits or MSB 8 bits, and lower 2 bits will be returned to this particular DCB0 and DCB1. Okay, these 2 bits are returned to this. Okay, so here we can set the duty cycle in the range of 0 to 1024, because here 2 raised to 10 is equal to 1024. These particular modes are available for duty cycle. Okay, values are available for duty cycle. Here you can see output pin configuration RC2. If I am going to use CCP2 module, then I should write in this way: 3C bits dot RC2 is equal to 0 0. If whole port I need to configure as a output port, then I will write 3C is equal to 0 cross 0 0. Okay, and along with this pre-scaling option for timer 2. So timer 2 is written with value 0 cross 0F. Okay, initial value. If then we will set pre-scaling option, post-scaling option. We can write here. Here 1 has to 16 is considered, and in the last stage we will turn on the timer. Okay, by writing T2 con bits dot TMR2 on is equal to 1. Okay, this will turn on the timer 2. Okay, here you can see PWM mode you can configure by writing the value 0 0 CCP1 con is equal to 0 cross 0 C. Okay, higher bits will be 0 and 1 1 cross cross. Okay, so this particular mode will be selected PWM mode for CCP module, and here we will write TCB 1 B0 DCB 1 B1 is equal to 0 0. Okay, now these values we have considered for generating 4 kilohertz PWM frequency. Okay, with the period 2 register value is calculated for 20 megahertz and 4 kilohertz frequency respectively, that is oscillator frequency and PWM frequency 4E. This is the period register value that should be loaded into PR2 period register. Now if I want to set 20% duty cycle, that will have 20% on period and off period of 80%, then I should load this value CCP1 lower byte value is 0F and remaining bits are 10. Okay, so for 40% 01 this lower bits and value is 1F, 60% 2E lower byte register and 11 for this particular bits, 80% 3E and 10. Okay, these are the values. 100% we cannot set generally because 100% duty cycle is nothing but the single line that we can draw on the output. There will be no any off period. Okay, so we will use only 20%, 40%, 60% and 80%. Okay, by calculating these values. Okay, so remember 0F, 1F, 2E and 3E, these are the values for lower byte register that will be transferred to CCPR higher byte register whenever period of the PWM signal is ended. Okay, again these two lower bit values are written to these particular bits. Here you can see the circuit diagram. We will consider this circuit diagram for practical. Okay, so here you can see this is the DC motor that is interfaced with the PIC microcontroller. Okay, here you can see RC7 pin is connected to this driver IC L293D. Okay, and RC6 also is connected. So two inputs are given, and this is the RC2, that is the period which is given. Okay, so here we can generate, we can apply, we can drive this DC motor. Okay, by using this. Now this particular driver IC has two output modules. One, that means what, two motors we can drive by using this particular IC. Okay, so these are the minimum connections that are required. Okay, reset and crystal. Okay, and here you can see the driver, DC motor driver for this particular thing, DC motor driving. Okay, here output 3 and output 4 pins are connected with the DC motor to drive this DC motor. By setting the PWM mode, you can drive this DC motor. Okay, so here you can see again, once again I will we will repeat these steps of PWM operation for CCP module. Okay, set the PWM frequency and period by using these two resistors. So first we will set the period by writing PR2 value. Okay, then we will set the duty cycle by writing value to lower byte register and CCP1 con bits, that is 10-bit resolution. Then CCP1 pin we will make output by writing 0 value to trace bits dot trace is equal to 0. Okay, then RC6 and RC7 we will make it as output because here we are going to connect motor through L293D driver IC, and here we will set in the next step timer 2 prescaling value, and we will turn on the timer 2. Okay, and we will configure CCP1 module into PWM operation. Okay, so this is what all about PWM mode of CCP for PIC18F4550. Okay, and we can write program for this particular PWM model. Okay, thank you very much. In the next session we will study practical application of this particular PWM mode by writing program for driving the DC motor. Okay, thank you very much.